I'm Jérôme Sopoçko. I work at Askia. And I really thought it was going to be a good idea that AJ gave an introduction to AI. I really wanted to anchor the whole day in science, in mathematics, and not in magic. And that voluntarily backfired because then Bex and AJ thought it was a good idea that it should be me that gives the presentation. So if anybody's wondering, the dummy, it's me. So no presentation is complete without a quote by Saint David Bowie. You can run, you can hide, but you got to change. You got to embrace the strange, and the strange is AI. So, what is a large language model? It's just a simple way for computers to understand and generate text and images. For this to work, what they've done is they've made machines read the internet twice, pretty much like what Chuck Norris had to do, and also every book that they could get their hands on, legally or illegally, that's another thing. Some models have got different uses, we're going to go through them, but first I want to go back a little bit in history. In the beginning, when there were first attempts at artificial intelligence, we had expert systems. It was inspired by Bertrand Russell's approach to mathematics and Turing, meaning like enumeration leads to conclusion. So a prologue was a very good language I had to learn for those type of tasks. So rules are at the core of the idea. So you try to express the world in terms of rules, and then you draw conclusions. So if all cats have tails, and Felix is a cat, Felix has a tail. It gets a bit more complicated if, for instance, Beck says AJ is a cool cat, and he is. And does that mean that AJ's got a tail? And I don't think it does. I didn't check properly, but so what they did after that is introduce like fuzzy logic, probability that any fact is true. So if you remove the bloody door slamming incidents involving cats and their tails and the cats in the Isle of Man, you can say that 90% of cats have got tails. And if we look at what Beck says, 50% is true, generally. She's really good at market research. She's not very reliable about judging people. That's what she asked me to speak. So then you can infer that AJ's got 45% chance of having a tail. So the problem with that, of course, is the fact that it's very hard to assess those probabilities, almost impossible, and they change depending on the speaker, depending on the subject. And language is way too imprecise to be turned into rules. So although expert systems led to some interesting stuff, and still used today, it was pretty much a dead end. The other way of approaching language is the Noah Chomsky's approach, where you try to build a model. Apparently, we're all born with the model of grammar, and it's the language we acquire is just a development of that model. But again, although that got really mathematically intense very, very quickly, the language was too imprecise. You had a problem with rock, which is a stone, but also a movement of music that some young people like. You got rose, which is the path of to rise, and it's also a flower. And worse than that, there was the almost unsolvable problem of pronouns. In that case, you can see that the dog ate the bone because it was. You need to have the last thing. You need to know if to know what it means, delicious or hungry. So you need to understand language to have a database of facts to understand what's happening. And that proved to be a pretty much unsurmountable task. So we had to look at other solutions. The revolution came, apparently it was a Turing idea, but it was inspired by biology. In the brain, we got neurons and synapses, And the information flows through electricity from one neuron where there's a quantity of information. Depending on the strength of the synapses, it gets propagated to other neurons, and there's another neuron, etc., etc., etc. After reinforced learning, you've all heard about the Pavlovian dog. If we repeat the, ringing a bell and feeding the dog, after a while it's going to salivate. Why? Because those synapses got a strong connection between the noise and the reaction. So they built a model where there was an input layer, and in there you can put survey data or anything. So survey data, it could be how much somebody is earning, how much they are in debt, how much they spend, and other thing. You put into the model, and you got a decision, can I lend him some money? And at what rate? And which percentage of the house? And then in the end, this in Y1, Y2, Y3, the output layer, you're going to get a probability of that decision getting correct. When you don't get the right result, and of course you don't, you slightly change the model. It's called rewarding the model, but actually what we're going to do is punish it. We're going to look at the expected result and compare to the actual result. That's the error. And by looking to every single of those lines independently, we're going to look at the gradient of the error. We're going to do, sorry, it's a bit of math, partial derivatives for each of them. And thanks to that, if we imagine that we want to improve the model just a little bit, by how much should we change any of those connections, any of those synapses. And that's the foundation of modern AI. You've got it here entirely. By repeating this, a lot of times the model is going to get better. It's going to find a local maximum. And this is called assisted learning. One interesting thing is you can put images in there where you got pixels, and in the end, you're going to recognize that 3 is not an 8. And there, what we've done is managed to reproduce through technology something that we have in our brain. We are very good at recognizing faces everywhere. We see them in clouds. We see them in trees. People see the face of Jesus Christ on a half-burned piece of toast. And it's something that's interesting. What's more interesting is we need to understand in biology, but also in artificial intelligence, what happens in those layers. And that's a very active area of research where we try to understand not just why it works, not just why it's a black box that works, but what's inside the brain and what's inside the model. Then in the mid to late 80s, the winter of AI happened. We could recognize a few handwritten numbers, maybe a cat, maybe a zebra, but not much was happening. And that's when I decided to change my major from computer and artificial intelligence to statistics. I'm still kicking myself. But at the same time, the computers got more and more powerful. All of a sudden, we could have millions of those synapses that could be in a model. And all of a sudden, AI won at Go, not by enumerating options, but by deep learning. So, how it happened, this generative AI? Just by playing a simple game. What is the next word? To be or not to be? And if we look at an example like the cat sat on the, we got a lot of options in English language. And we can imagine that what we're going to do is rank all the possible options by order. Mat is at maybe 20%. We're going to have fridge at 10%. And rug is a possible option as well. Spaceship is near 0. And the cat sat on the, that's impossible. So what we do is we rank this, and we do a Monte Carlo simulation. We pick a random number, and depending on those probabilities, we pick the one of the most likely. And then we generate another one, and another one, and another one. That's it. That's all we do with generative AI. So, to know if a word is a good probability, that what we need to know is look at it in context. And that's why we need to train the model, and we make it to read a lot of things. And we see that work in its context, and then we can build an idea of how it's used, which words in proximity or near proximity, and also which ones it's never used with. And thanks to that, we build like a vector of values, a profile of that word. It's sometimes called a word embedding. And we can see if we do that with other words that, I hope you can read it, that sea and ocean are pretty close in their profile. You say lost at sea, not lost at ocean, but it's pretty cool. Football and soccer, when in the end they're both sports, well, there's ambiguity about it, but let's not have a go at Americans right now. But I and we as well are quite close because they're pronouns and it can be used in a very similar way. The main discovery was done by some guys at Google in 2017. There's a paper that's called "Attention is All You Need," and what they've done is looked at words instead of running them sequentially and putting them in a recurrent neural network. They looked at the importance of each word compared to each other, and that's what they call self-attention. And they found a way to put all those words together in one go with their self-importance, and that's what is called a transformer. The article is almost readable. You can have a go at it. And thanks to that, you can see that there's a difference. Interest could be a love interest, but it could be like a financial thing. And thanks to that, it was much easier to differentiate between concepts. Incredibly, Google dropped the ball, and OpenAI picked it up. And Microsoft is going to probably, you've all heard about what happened this weekend. But what they did is created something called GPT, a generative, pre-trained, because lots of text, transformer. That's the key word. They create the first model, GPT-1, and had lots of parameters, and roughly multiply by 10 and by 100 the number of parameters to the level it is now. And all of a sudden, they realized that they had like something I didn't expect, an emerging behavior. The model was very good at summarizing text in the style of Shakespeare, of Leonard Cohen, of whatever you wanted it to be. But it was not good at replying to a prompt. If you say, Paris is the capital of France, it could talk about other capitals and not talk about France, which is maybe what you wanted it to talk about. So what they did is 3 things to improve the model. They wrote 12,500 prompts with their answers. Things like, explain to a 7-year-old how gravity works. And somebody had to write that. That was expensive, so they thought, we need a better way. What they did is ask the GPT to give 31,000 questions to give 10 replies, and then they ranked those replies. It was much easier to do, and thanks to that, they had a classifier of what is a good reply to a prompt. And thanks to that classifier, then they could improve the model. And that's why GPT 3.5 appeared and was so good at reply to prompt. After that, what they did is for ChatGPT, they put in conversations. So again, repeating the process and seeing how it works. And that's why also in the model, you can see if you use ChatGPT, you can say, is the response good or bad? Because they are constantly trying to improve the model thanks to your input. So now the small prints in the generative AI contract. They have no idea of the truth. They don't care. They're pretty vacant to, in other words, they can lie, and that's called an hallucination. There's active ways of doing that. The way to do it is, of course, to check the results compared to a database of facts with Open Graph and lots of things. Very active area of research. You're going to have a new skill. The skill is to write prompts. You will not be replaced by AI. You will be replaced by somebody that uses AI and that can write prompts really well. So that's the skill you need to acquire now. So Here are some of the areas where generative AI can be used: text, image, music, code. I use it daily. Of course, I've left overthrowing the human race and building the matrix, but you know it's coming. I'm going to go quickly now. That's what AI is currently, really good at for what we do. And this is how we use it at Ipsos. At Ipsos, what we've done is we built a sandbox, like a private model of the data where we can put our clients' data and we're not afraid that it's going to leak. And these are the things that we currently work on. We're currently also actively working on generating surveys, questionnaires, not yet data, but we're going to talk about that later. And finally, how it's used in our industry. Again, that's the whole point of this paper. So right now it's doing things faster and better, but creativity is going to get in place. I, for one, think it's going to be very interesting. That's it for me. I hope I've given you like a good introduction. You know now how it's done. You're almost ready to program it. I've got to thank a lot of people, but I've given 2 links here which are fantastic, and I've paraphrased in this presentation. You have them in the papers. All the illustrations, of course, are done by Dali, or most of them, except David Bowie. Thank you, Richard. Thank you.